Okay, in the last lecture, we discussed about the mathematical model of cold wire injection in steel melt, and there basically we discussed some of the results of the mathematical model, that is the melting sequence of the cold wire into the liquid steel, that is what is the mechanism of melting of cold wire in the liquid steel, and also we discussed about the distance traversed by the wire in the liquid steel. And that is very important because liquid steel, as you know, is very opaque and you cannot see where the wire is going and where it is melting. So, it is very difficult to know where the wire is melting exactly. As we have said, there is if the wire melts at the bottom of the ladle, then the powder is released at the bottom of the bottom of the ladle, then powder will take sufficient time during the rise for assimilation into the liquid steel. Okay, so it is very important to calculate where the wire is melting. Okay, so this thing we have basically the model has the capability of predicting where the wire is melting, and we can assume there is the powder is released at that point. Okay, so in this lecture basically what we will be doing, this is the industrial application, as I said, or is the industrial implication. That means how we can use these results of this model for industrial applications. So, first thing that will be discussed here is the mapping of the distance traversed by the wire against the industrial operating condition, because in industry the operating parameters changes widely, and under wide industrial operating condition where the wire is exactly melting and the powder is getting released, that will calculate and will show some results. And also we will correlate this distance traversed by the wire in the liquid steel with the estimated calcium recovery. That is the most important, because finally where the wire is melting, where the powder is getting released, and why we are doing all these things only to have an effect on the recovery, because recovery is the most important point, that is we want to calculate. So, we need to correlate the calcium recovery with the distance traversed by the wire in the liquid steel. And then we will also discuss there is the estimate the wear addition, how much wear actually is needed, because in industry since we do not know the optimum operating parameter for maximum calcium recovery, we just arbitrarily use the amount of wear addition. So, we do not have any ideas, and most of the cases we add much more wear that is needed. And if you add the more wear, then also it has some problem, because the calcium in the bath will be very high and that may not lead to a very good inclusion. Okay, so a optimum amount of wear has to be injected into the bath, and also the operating parameter should be such that the calcium recovery is maximum, such that we can make a save of the wear and also generate the proper inclusion. Okay, so this is first result. We have basically calculated the distance traversed by the wire against wear speed, that is the 100 to 300 meter per second. This is the industry, this is the range in which the industry uses the speed of the wire. Okay. And also you can see the bath superheat exactly is not constant, and the bath superheat also varies between 1560 to 1625, that is by 75 degree the bath superheat is also varied. Under this condition, so for different heats in this operating range, we have calculated what is the distance traversed by the wire by our model, and you can see the symbols. This symbol basically indicate there is the distance traversed by the wire under different operating condition. For example, at a wear speed of 150 and some bath superheat, what is the in this range, this is the values. So, what you can see from here, that the distance traversed by the wire with the wear speed also passes through an optimum, that you can find, that is this passes through an optimum and then decreases. This is for the calcium silicide wire, and this is for the cafe wire. And in case also we can find there is a nice, there is at a particular speed around 200 meter, you can find it passes through a maximum recovery, okay, and that is the maximum distance traversed by the wear. So, this is what we discussed in the previous lectures also from the mathematical model, that is the wear distance traversed by the wear become the maximum at a optimum speed, not at low speed, not at high speed, okay. So, there should be an optimum speed, okay. This we have discussed already. So, this is followed in industrial results also, but most interestingly you can find this is the ladle bottom and most of the data point rise above the ladle bottom. What does it mean? That is the distance traversed by the wear in most of the industrial heat exceeds the ladle bottom, and that in other words it means that is the wear does not melt even after reaching the bottom of the ladle. So, what happens? I do not know, actually it can spiral there, something happens, it is not melting and it melts much after time. So, that basically will reduce the recovery, okay. So, anyway that we will see whether it reduces the recovery. And you can see that is some of the cases only distance traversed in these regions, that is the wear melts just at the bottom here and here, okay. So, you can find, and most of the cases you can find it does not melt even after reaching the bottom, that is the wear exceeds the wear bottom, that is the wear exceeds the ladle bottom, but still it does not melt. Now, if you see the cafe case, in cafe case there are some cases where there is a premature melting, this is the ladle bottom, before reaching the ladle bottom you can find the wear gets melt, okay. And in some cases, that is even after reaching the ladle bottom the wear does not melt. So, in case of cafe both the things can happen, there is a premature melting or delayed melting, even after reaching the bottom it is not melting. In case of the calci, in most of the cases it is delayed melting, that is it does not melt even after reaching the bottom. So, this is the two major observations that we can find, that you have tell here there is the traveling a maximum that at an optimum speed that is observed, and wide range, there is under wide range of operating parameters predicted in the industry. The distance traversed by the calci wear mostly exceeds the ladle bottom, while cafe data remained on either side of the ladle bottom, that is premature melting or the does not melt even after reaching the bottom. This is the similar plot, here distance traversed with the bath super heat I have plotted, and where speed range is this 110 to 280 centimeter per second, in this wide speed range is there, and then all the data we have plotted. And we can see with the bath superheat basically distance traversed decreases, that is expected, and mathematical model also showed it is really decreases in both the cases. And we can see in case of the cafe there is both the premature and the premature melting as well as delayed melting, and in case of the calci it is mostly that is the delayed melting, that is delayed melting mean even after reaching the bottom the wear does not melt. So, and it is decreasing as you can find. Some of the you can see is just so distance traversed by the wear decreased with increase in bath superheat as expected, and in most of the cases the distance traversed by the wear exceeds the ladle bottom for calci, that you can find all the data above the ladle bottom. For cafe it is on either side of the ladle bottom, that is premature melting or delayed melting both, and only in very few cases the wear melt just at the bottom, and there you can expect the maximum recovery. That is why we have done next figure that you are going to see, there we have correlated the estimated recovery with the distance traversed by the wear. But before that, let us see how do we estimate the calcium recovery. This is the way we have calculated the calcium recovery, simple mass balance on the still, liquid still. So, we have taken two samples before calcium injection and after calcium injection. So, the calcium recovery is defined, that is the calcium final minus the calcium initial, that is initial means before the start of the calcium wear, and final means just after there is the calcium wear injection is over, then you take a sample, that is the final. So, this minus this divided by the calcium added, this is the total calcium added. Added means there is the wear is added, what is the length of the wear that you have added, and how much there is the how much calcium silicide powder is there per unit length of the wear. So, we can easily calculate how much calcium is added. So then we can calculate the calcium recovery, simple thing. Now again here you can see there is the recovery has been plotted against the distance traversed by the code where this is predicted, okay, and this is the estimated recovery. Excellent. And you can find in case of calcium silicide, you can find what you can find, that is within the distance traversed, as you can see when the where melts just near the bottom, okay, in this data you can see the recovery is maximum. As the distance traversed by the wear for delayed melting, that is when the wear does not melt even after reaching the bottom, in those cases you can find that is the recovery is less, and recovery become lesser and lesser as the distance traversed by the wear increases beyond the ladle bottom, and that is expected, you can see. So it is very nice data, that is the industrial data shows that the recovery really become maximum when the wear melts just at the ladle bottom. So at the ladle bottom. Similarly, in the cafe also you can see the recovery becomes maximum when it melts at the ladle bottom. On either side, the recovery is less. So calcium recovery decreases both for premature melting and the delayed melting beyond the ladle bottom that we can find. Calcium recovery of calcium silicide could be as high as 20 to 30% when the wear melts at the ladle bottom. So you can find here the recovery is 20 to 30% you can find when the wear is melting just at the ladle bottom. And also if you can see in case of the cafe, you can see the maximum value is around 6, calcium recovery is only 6, that is the cafe, that is the wear, depending on that thing. So calcium silicide has a better recovery than the cafe. There is the maximum recovery at the ladle bottom is 20 to 30, in this case only 6, okay. And calcium recovery of calcium silicide wear reaches a low value of 5 only under unfavorable operating condition. You can see when the operating condition is not good and the distance traversed by the wear exceed much beyond the ladle bottom, that is around say 7 meter. So in that case the recovery can reach around 5 only 5. So it can be maximum 20 to 30 and it can reach even a 5% recovery if your operating condition is not favorable. Similar thing you can find also in this case in cafe also. Cafe inherently has very less recovery, but again if you have a premature melting or delayed melting, in both the cases recovery further goes down, okay. Now another thing, very important thing, mapping of the wear injection operating parameter for stable casting, that is stable casting means, as you know, that is during the calcium injection is done basically for stable casting as well as for the inclusion modification. Stable casting is when you can make the casting uninterruptedly. Interruption can take place if suddenly the supply of the liquid become less, then the casting can be very unstable, because the liquid always has to be supplied at a constant speed to the continuous caster. But if the speed of liquid flow into the continuous caster suddenly decreases, the casting will be destabilized, because you are extracting the heat in continuous casting at a particular rate. So your speed of liquid, that is the liquid flow rate into the continuous casting mold, has to be constant. But sometimes it gets affected. How? One of the reason is due to the inclusion only, because of, in case of the calcium killed steel, aluminum killed steel, you will have this type of instability sometimes occurs because of alumina inclusions, because alumina inclusion has a tendency of aggregation and they can block the nozzle. They can attach to the that is the wall surface and make an agglomerations, and then they can block the nozzles, and that is called the clogging of the nozzle. Okay, this aluminum is very notorious for doing this job. But if you treat the aluminum killed steel with calcium in an optimum manner, okay, such that the product become a liquid calcium aluminate, then you can eliminate this, because aluminum inclusions are solid inclusion, very refractory oxide and does not melt even at the steel making temperature, and they have a surface characteristic. They try to agglomerate and then they clog the nozzle. And if you can make a calcium aluminate by adding calcium, and that is liquid at steel making temperature, you can convert that solid alumina inclusion into a liquid inclusion, and then they can coalesce, join and then float to the slag and get rid of the system, and then this instability will not occur. Okay, for that thing it is very important what is the composition. There is the calcium, aluminum and sulfur composition. Sulfur is also very important parameter, because sulfur, that is, if you have a sulfur, then calcium will first form the calcium sulfide. It is a very strong compound. Okay. So, calcium sulfide, calcium aluminate, all combination. Okay. So, and some of the aluminate, calcium aluminate, all the calcium aluminate are not liquid at steel making temperature. Some of the calcium aluminate are solid at steel making temperature. So, if you have a ternary diagram with calcium, aluminum and sulfur, there are certain composition in which you will have a product which is liquid at steel making temperature, and that will give a hassle free casting. Okay. So, in this ternary diagram you can find in this range, if your composition lies in this range, then you are supposed to get a stable casting. That is the calcium aluminate or sulfide, whatever is formed, they will be in the liquid state. Okay. Or they will not. Basically, if the composition is here in this range, you will find a very stable casting. If the composition lies across the calcium vertical, that is, if it is a calcium rich inclusion, okay, if you have a calcium rich inclusion, then it can lead to the ladle gate erosion, because if your calcium is high, then the most of the cases the ladle gate is made of alumina. So, alumina may dissolve because of higher calcium, and then you can have ladle gate erosion. And another case is there, if your inclusion is rich in aluminum. Rich in aluminum means you will give the clogging, because it is the alumina rich inclusions. So, calcium is not sufficient. So, in that case, those calcium aluminate whatever form are usually solid at steel making temperature. Aluminum rich calcium aluminate are usually solid at steel making temperature. So, they will give the nozzle clogging. So, you can study this thing in terms of ternary diagram also. This is taken from the Story et al. They have studied from different plant data, and this is the mapping. So, instead we can also, how I have studied here, instead of doing that ternary, we have done it by calcium to aluminum ratio. There is the modified CAL ratio. This is also literature, people also done. And you can define this ratio in this form, calcium minus S minus 2 by aluminum. Why you have subtracting this term? Because whatever the sulfur, amount of sulfur is there, you have to subtract first, because the sulfur, in presence of sulfur, calcium will form a calcium sulfide, which is a very strong compound. So, you have to eliminate that. That much of calcium will go with the sulfur. So, I am eliminating that sulfur, and 2 is basically the solubility of sulfur in the calcium aluminate, that also I have to decrease. So, then whatever the calcium left out, that calcium basically will participate into the formation of calcium aluminate. So, this Ca by L ratio will give you an idea what type of calcium aluminate is going to form based on their atomic ratio. So, this definition we have given, I have just talked about. So, and if this Ca to L ratio in the range of 0.5 to 1.5, then the inclusions forms are liquid, okay, and they will not form the nozzle stable casting, they will give the stable casting. So, that is why we have characterizing of inclusion based on the CAL ratio. So, here we have plotted the modified Ca to L ratio, and in this type all the inclusion that we get from industrial operating conditions. Okay. So, you can find that whatever all this inclusion we have got from industry, and in this wide operating range, there is the wear speed 50 to 90 meter per second, and bath super is 86 to 110 degrees centigrade. In this range we have collected all these inclusions. That is the sample, we have taken the sample and we studied the inclusions, and you can find that if the Ca to L ratio is 0.5 to 1.5, then stable casting, and this much of data are falling under this category. And you can find there are two type of symbol, one is dark, another is light. Light is basically after recommendation. We have made some recommendation. First, all the dark point you consider. So, these dark point are often under this wide operating condition, and the modified Ca to L ratio lies in this range. Okay. So, you can find the sample lies all over the range. There are some samples are there in the clogging range, that means which is the alumina rich inclusions, and some inclusions are there in the stable range where the calcium aluminate forms as liquid, and there are some inclusion in this range, that is the calcium rich inclusions. Okay. So, those are basically the ladle gate erosion, because aluminum dissolved into the bath. So, ladle gate erosion takes place. So, these are the data we got. Then we calculated, that is what should be the operating parameter for which the calcium recovery is maximum, and how much aluminum has to be added such that our Ca by Al2 ratio remains between 0.5 to 1.5. Based on this calculation, we prescribe them, that is you add this much of wear, under this operating condition you add this much of wear instead of what you are adding this wear. So, sometimes we prescribe little higher addition of wear and sometimes little less addition of wear. If you can do that, after doing that, after recommendation you can find some of the symbols, that is the light symbols are coming here. So, all from the ladle gate erosion, all the samples, now all the inclusion come under this stable casting region and some in the clogging region, a few 1, 2, 3. So, most of the samples now come under the stable casting regions. So, it is possible, that is if you can analyze, if you know where the wear is melting and what is the recovery level, that you know, because under this wide operating condition you can simply calculate where the wear is melting, and then you can know what is under this melting under this condition what is the recovery, that also you know. If you know the recovery, then to get an optimum amount of Ca to L ratio, that is the Ca to L ratio to get 0.5 to 1.5 in this range, how much aluminum has to be, how much more calcium has to be there, or how much calcium has to be deducted from the sample, that you know. So, based on that you can estimate how much wear is optimum amount of wear that must be added such that Ca to L ratio under this condition become 0.5 to 1.5 range. So, based on that we advise them to add the calcium wear addition, and they did that, and we can find that is the most of the data point are now in the stable casting range. Okay. Now, after doing this, we have done another work, and in this case it is with the Tata Steel, and previous work with the Vizag Steel, and this is with the Tata Steel we did, and this is the Bosak et al. Bosak, there is a PhD student worked with me. It is little earlier work, and the work that I presented is most recent one. In this work what we did, basically we also estimated the calcium recovery and correlated with different operating parameter in the form of dimensionless number. That is with the Biot number, that is the dimensionless heat transfer coefficient in the thermal boundary layer. It is very important, the Biot number, higher the Biot number, higher is the heat transfer to the wear. There is the wear liquid interface. The heat conductance is defined by heat transfer coefficient. So, if heat transfer coefficient is high, your so there is the heat flux through the wear will be more. So, Biot number basically gives you the thermal conductance through the thermal boundary layer, and theta is the dimensionless temperature, and as well as we have another dimensionless number we have considered, that is relative rate of silicon to sulfur transfer. Thing is that when the calcium silicide powder is added, and when the calcium silicide powder is get exposed to the liquid still, then the silicon will try to migrate from the calcium silicide to the liquid bath, depending on the bath silicon composition. If the bath silicon is less than that of the in the calcium silicide, obviously the weight percent of silicon is much higher. So, silicon will try to move from the, that is the powder, to the liquid bath. At the same time, sulfur also will try to move from the bath to the powder surface. Okay. And if you consider there is the mass transfer across the concentration boundary layer around the powder is the rate limiting step, then we can define that is the relative rate of silicon to sulfur transfer. Okay. Now, mass flux through the concentration boundary layer, that is for silicon, we can define by this square root of d into delta Ci. Delta CSI means that is the concentration of silicon at the powder interface and the concentration minus the concentration of silicon in the bulk. Okay. And so, it is basically that is the surface renewal theory or Higgs penetration theory. This you can calculate the mass transfer coefficient that is directly proportional to square root of d, that is the molecular diffusivity of silicon. Similarly, for sulfur, this so numerator gives you the flux of silicon from the powder surface to the bulk. Similarly, denominator represents there is the flux of the sulfur from the bulk to the your powder interface. So, higher will be the rate, that is the rate of depletion of silicon will be much higher. If NR is high, that means depletion of silicon or the transport of silicon from the surface to the bulk is much higher compared to the transfer of sulfur from the bulk to the interface. And that is not a good thing basically. If the calcium get depleted of silicon fast, its vapor pressure will go on increasing. In fact, calcium silicide is injected in the form, that is the calcium is injected in the form of in a alloyed form only to reduce the activity of calcium into calcium silicide, because otherwise calcium is very volatile. Its vapor pressure is more than 1 atmospheric pressure, instantaneously it form the bubble and go away from the system. If you give silicon, if you alloy it with the silicon, then activity of calcium will be less and the partial pressure of calcium will be much less than 1 atmospheric pressure even at 1600 degrees centigrade. So, it will not go away as a vapor. But if the silicon transfer from the powder to the bath is much faster, in that case as the silicon get depleted into the powder, the calcium activity will increase, its vapor pressure will go on increasing. So, if the silicon transfer is much faster compared to the sulfur transfer, if the sulfur come and combine with the calcium, that is a much more strong compound, in that case the activity of calcium will not decrease, okay, because silicon is leaving but the sulfur is coming and it is combining with the calcium forming the calcium sulfide, and that can be retained. Okay. So, this lower this ratio, that basically will enhance the recovery. So, anyway we have, you can see that is why it is negative, its recovery increases with the negative of this term, that is fine. Okay, all of this, obviously the conductance, that is the, if your H is very high, that means rate of heat transfer is faster, where will melt much faster, the premature melting can take place. So, that is why the negative sign here also, negative exponent is there also. And the way we have defined the temperature, there is the bulk temperature by superheat. Okay. So, where the bulk temperature, there is the bulk temperature is higher, then the rate of heat transfer is first and then premature melting can take place. So, there is some. So, anyway, so this is the correlation with the your Tata Steel data, and the recovery is correlated like this, and you can find there is a good relationship. Now, another most interesting thing that we have found is that X-ray mapping of the impurities of inclusions. We have mapped the inclusions at different speed, 150 meter per minute, wear speed of 150 meter per minute, then 200 meter per minute, 250 meter per minute. But we found that the best inclusion form only at 150 meter per minute. So, we have just X-ray mapping you can find, and what you can find is the oxygen, aluminum you can find. So, it shows that is the inclusion is aluminate. So, aluminum is there, oxygen is there, calcium is there. So, it is basically calcium aluminate, silicate also, some silicon is also there, calcium aluminum silicate. And what you can find, then you can find there is the nice sulfur ring, that you can find, there is a nice sulfur ring. As I said before also, that is the a good modified inclusion will have a sulfur, because sulfur ring, because all the stringers, calcium sulfide, manganese sulfide, they will accumulate on the spherical calcium aluminate, okay, and they will finally form a very soft deformable calcium oxysulfide, where the sulfur will be at the ring. So, that is there. So, we can find at 150 meter per minute we can produce the best inclusion. So, this modified inclusion, as I said, they will not hamper that is the inclusion modification. This case we are talking about the inclusion modification. That is, if we cannot eliminate some of the inclusions, then we have to modify them. That is, we have to change their morphology, composition in such a way such that they do not hamper the further mechanical processing of the material. Okay, so that type of inclusion we want to develop, right. Now, what we can find, see, that is the calcium recovery is highest. If this is at 200 meter per minute. At this wire feeding rate, we found that calcium recovery is maximum. Okay. And then the calcium level in the bath was 20 to 35 ppm. Okay. But the suitable inclusion form at a lower speed, at 150 meter per minute wire feeding rate, where the calcium recovery is 15 to 20 ppm. That means, in the bath we need actually 15 to 20 ppm of calcium. We do not need 20 to 35, because that is in excess. So, only with this amount of calcium in the bath we can form the best inclusion, but the recovery is not maximum at this speed. So, what should we do? We should operate at 200 meter per minute such that we can get the maximum recovery, but we do not require that much of calcium in the bath. So, what should we do? We will basically reduce some amount of wear. I will reduce some amount of wear, but I will increase the recovery. That is the thing. So, if I want to reduce, that is, if you say average 27.5% wear to average value 15 to 20, 17.5 ppm. So, I want to bring down the calcium from this level to this level. So, a calculation shows the 100 meter wear I can just save if I operate with 200 meter per minute, because at 150 meter per minute I had to add more calcium to get 15 to 20 ppm of calcium in the bath. So, now with 200 meter per minute if I inject, then the recovery will be maximum. So, I can reduce some amount of wear addition. So, considering a normal wear addition of 300 meter, this leads to a saving of 100 meter, that means 33% in the calcium powder. So, it was an interesting result. So, if I operate at an optimum operating condition, then my recovery will be maximum. In that case, I can reduce lot of wear addition such that I can get an optimum level of calcium in the bath. Okay. So, in industry that is happens. In most of the cases, they add much amount of wear. In some cases, their recovery is very less. Okay, that is why they have to add too much of wear. Okay. So, that is the thing. So, these are the reference, basically reference is our paper only, this is, and the Story et al, right. Story has made the pioneering work on this. So, in conclusion, that is the what we did, basically model predicted distance traversed by the wear is correlated with the calcium recovery, wear speed and the bath superheat. So, we have seen that under industrial operating condition, in most of the cases, that is the wear addition, the operating condition is such that the wear does not melt even after reaching the bottom. In most of the cases where there is a delayed melting, that is the wear does not melt even after reaching the bottom of the ladle. And in case of the cafe, it can be both premature melting as well as delayed melting. So, another point we have seen, that is the recovery. When we estimate the recovery, we find that indeed the recovery become maximum when the wear melt just at the ladle bottom. That time the recovery is maximum. So, it is proven with so far it was a speculation, that is the when wear will melt just at the bottom, the recovery will be maximum, but we have shown industrial data also says the same thing. So, industrially estimated recovery also says when the wear melt just at the bottom, then the recovery is maximum. Okay. So, this thing has been proven, and so we have shown that there is the wear addition, there can be extensive saving in the wear addition if I can operate the industrial operation at an optimum condition, at the optimum operating parameters, because the recovery will be maximum, our wear addition will be less, much less, such that we can get an optimum bath calcium. Okay. Thank you very much.